Today we're going to be talking about solving systems of linear equations using substitution. And why would you want to use substitution instead of just graphing? Well, practically speaking, there's a lot of situations where just solving by graphing is going to be a pain. Like, let's say you had y is equal to 30 over 47x plus 2, and the other equation was y is equal to negative 1/3 x minus 3. I personally don't want to solve that by graphing. It's going to be a huge pain to graph, and chances are wherever it meets on the graph is going to be some funky fraction that I won't be able to tell from the graph anyways unless I extremely creatively did my axes. So whenever you have a situation like that, you really want to have some algebraic methods instead. And one of the nicest algebraic methods is substitution. And what's the basic logic we use for substitution? What we're basically doing is saying that if I know 3 plus 2 is equal to 5, and I know 4 plus 1 is also equal to 5, that means 3 plus 2 has to equal 4 plus 1. This is known as the transitive property in mathematics, which is just a very fancy way of saying exactly this logic. That you know if A is equal to B and A is equal to C, that means B has to equal C. What you actually just did there is substituted in that if I know A is equal to C, everywhere I see an A, I can replace it with C. Similarly, if I know 4 plus 1 is equal to 5, then that means that everywhere I see a 5, I can replace it with 4 plus 1. We're just going to be doing that with variables instead. So let's look at a more concrete example. So if you're going to be solving with substitution, you want to make sure that your equations are set up so that it just says variable equals stuff for at least one of the two equations. Doesn't matter which one, but as long as at least one of the two is that way, you're good. Then you want to substitute in that expression into the other equation. So what do we mean by that? So in particular in this equation, I know that if x is equal to y plus 1, everywhere I see an x, I can replace that with y plus 1 in parentheses. So let's go ahead and look at an example of that. So I can rewrite that first equation as y is equal to 4, leave some parentheses, plus 2. And instead of writing x, I'm going to write what x is equal to in the other equation, which is y plus 1. Then I want to go ahead and just solve this as a simple linear equation with one unknown. So I'm going to go ahead and in particular distribute the 4 to both of these. We get y is equal to 4y plus 4 plus 2. Then I want to combine any like terms within one side of an equal sign. So in this case, 4 plus 2 is going to give me 6. Now I'm ready to go to start moving stuff across the equal sign. I want to move all of my constants to the same side. In particular, I notice the left-hand side only has a constant while the right-hand side has both constants. Sorry, the left-hand side only has a variable. The right-hand side has both variables and constants. I want to move all my variables to the same side. Apologies, I might have said constants, although you also do want all constants on the same side. So I'm going to take away 4y from both sides. 4y minus 4y makes 0, and I'm left with negative 3y is equal to 6. And then as a last step, I will divide both sides by negative 3 to give me that y is negative 2. However, I'm not done. I still need to find the value of x. All I've confirmed here is that the y coordinate is going to be negative 2. How will I find x? Well, I want to substitute back into one of my two equations. I think the second one looks a little bit nicer, because I know that x is equal to negative 2 plus 1, so x is equal to negative 1. And then I will have just found my solution. So I already had this solved for having one equation written has one variable in terms of the other. In this case, actually both did. Then I want to substitute that expression into the second equation and make sure to use parentheses around that expression, particularly if it's not already isolated in the other equation. So x was not isolated in the other equation. I want to make sure that I'm using parentheses there. Solve the resulting single variable equation. Then we want to plug back in the solution into the original equations to find the second variable. We're going to write our solution as an ordered pair, and then what we haven't done yet is check our work. How do we check our work? I think the nicest way to is just to pick the other equation and double check that when you substitute those values in, that it's still true. So is it the case that the y value negative 2 is equal to 4 times the x value, which is negative 1, plus 2 as well? So we get negative 2 is equal to negative 4 plus 2. Negative 2 is equal to negative 2. That's a true statement. I did just check my work. Now keep in mind when you're solving that in the background, there's still these different types of solutions. So you might have a single solution like what we just found where it was just a single point that is going to work for both of these equations. No other unique pair of values is going to work in those equations except for that point. If you end up solving and you get a contradiction at the end, something like 0 equals 4, that's when you know that this is an inconsistent system. So what would be an example like that? So if you had something like y equals x plus 1 and y equals x plus 2 as your other equation, if you were to start solving this by substitution, you'd be like, great, both of these have y equals stuff. I'm going to substitute what y is equal to into my other equation. So then I get x plus 2 is equal to x plus 1. So what I did was I substituted in what the value of y was in the other equation. Then as I start solving, I would subtract x in order to get all of my variables on one side. And I get 2 equals 1 at the end, which is not true. So in that case, that would be no solution. As soon as you find that all your variables went away and you're left with something that's a contradiction, aka a false statement, you know you have a no solution situation. Versus infinite number of solutions, again, is going to happen when it's really just the same equation written two different ways. And you'll find when you're solving it that all of your variables disappear and you're left with a true statement such as 6 equals 6. So an example of that, let me sort of differentiate it, would be something along the lines if I had y equals x plus 1 as one equation, and then I had 2y equals 2x plus 2 as the other equation. Well, I would say, okay, well, I can replace y with what he's equal to. So as I'm doing that in my second equation here, I'm going to get 2 parentheses equals 2x plus 2. And what am I going to get put in that parentheses? The other value that y is equal to, which is x plus 1. Then I would start to solve. I would do 2 times x is 2x, 2 times 1 is 2, equals 2x plus 2. You might already notice that this is getting a little bit silly because then when I subtract 2x from both sides in order to move them all to the same side, I guess 2 equals 2, which is a true statement. So in this case, this would be infinite solutions. While in the other case, this would have been no solution. So that's always something to keep in mind. So let's go ahead and do some practice problems. I think I've given you enough information that you should hopefully feel comfortable practicing this a little bit yourself. So I'm going to encourage you to pause your video and try these 2 practice problems, and then we'll go over it together. So in this first one, they're just asking, is this a solution? Don't overcomplicate your life. It's just confirming if it works for both equations. You don't actually have to find out what the solution is if it's not this. So if we're going to find out it's the solution, that means that it needs to work inside both equations. So let's just plug into the first one first. So substituting in y is 4 equals 7/4 times x is going to be 2 plus 1/2. So all I did was replace everywhere I saw an x with 2, everywhere I saw a y with 4. And then we're going to go ahead and start to solve. So 4 equals, and then keep in mind this 2 is secretly over 1. And we're going to multiply across the top, multiply across the bottom. 7 times 2 is 14 over 4 plus 1/2. If I want to continue to simplify the right-hand side, these need to have like denominators. So I'm going to take the 1/2 and multiply both the numerator and denominator by 2. So that will simplify to 4 is equal to 14/4 plus 2/4. 14/4 plus 2/4 is going to make 16/4. And 16 divided by 4 simplifies to 4. So that is a true statement for that equation. Let's go ahead and check the second equation as well. So the second equation is negative x minus 8y is equal to negative 35. What are we substituting in for x? That would be 2. What are we substituting in for y? That would be 4. Let's go ahead and start to simplify this. Negative 1 times 2 gets us negative 2. Negative 8 times 4 gets us negative 32 equals negative 35. Negative 2 minus 32, negative 34 does not equal negative 35, so it is not a solution to that set of equations for exactly that reason. So even though it worked with one of the equations, the fact that it did not work with the other equation means it's not a solution to the full system. Let's go ahead and try this next one, which is where we are actually finding the solution. So if we're going to find the solution, we're going to utilize the fact they already gave us y being isolated in the first line to substitute for y in the second line. So we have negative 20x minus 4y is equal to negative 20, but rather than writing 4y, we're going to write what y is equal to, which is negative 5x plus 5. We've substituted in the first equation into the second. Now I'm going to go ahead and just pretend this is a simple linear equation with one unknown. So I'm going to go ahead and distribute the negative 4. Negative 4 times negative 5 gets us positive 20x. Negative 4 times positive 5 gets us minus 20. And then I'm going to just drop down the rest of this. And that was a plus 20x, because remember, negative 4 times negative 5 gave us a positive 20x. I really should have written that plus initially. Now if we keep on going, combine like terms within one side of an equal sign. Negative 20 plus positive 20 is going to make 0 x's. Minus 20 is equal to negative 20. And negative 20 does indeed always equal negative 20. So because this is a true statement and all of our x's went away, this would be considered infinitely, I don't know how to spell today, infinitely many solutions, aka consistent but dependent, because this is really just the same line written twice, which we can confirm because if we were to solve for y in the second equation, it better end up giving us the first equation. So in particular, if I were to add 20x to both sides, negative 4y is equal to positive 20x minus 20, and then continue to get y by itself by dividing by negative 4 on all three terms. That would give us y is equal to negative 5x plus 5. So indeed it was the case that these were just the same equation written two different ways. So with that in mind, go ahead and see if you can solve this next equation yourself, keeping in mind that you'll probably need to rearrange one of the equations first so that either x or y is isolated. So if I was going to solve this, I think in particular the second equation is going to be a lot nicer to solve for, because then if I have negative 7x plus y is 41, if I want to get y by itself, I would add 7x to both sides. Negative 7 plus 7x makes 0. I'm left with y is equal to 7x plus 41, and that gives me something that in the first equation, 5x plus 2y equals negative 13. I now have a value I can substitute in to y, and I'm also going to just, for illustration purposes, rewrite y also as purple. So if I'm going to do that, the 5x plus 2 times something that y is equal to is negative 13, and then I'm going to replace what y is equal to with that 7x plus 41. Now I'm good to go on solving, so I'm going to distribute the 2 to both of these terms. 2 times 7x gets us 14x, 2 times 41 gets us 82. Drop down the 5x, drop down the negative 13. Now I want to continue to combine like terms within one side of an equal sign. 5x plus 14x is going to make 19x. I'm going to drop down the plus 82 equals negative 13. I want to keep on going, so I need to move all constants to one side, all variables to the other. The left-hand side currently has a variable and a constant, while the right-hand side is only a constant. So the right-hand side is a good candidate to go ahead and subtract 82 from both sides. That gives us 19x is equal to negative 94. Then I want to go ahead and divide both sides by 19 in order to get x by itself. I have a conjecture that maybe 19 actually does go evenly into 94. Actually, I don't think it does. Oh, wait, no, I added wrong. Where did I just add wrong? Aha. 3 plus 2 is not 4, that is 5. And 19 definitely actually does go evenly into 95. In particular, 5 times. You might be wondering, how did I do that in my head so quickly? Well, 20 times 5 is 100. And then 100 minus 5 is 95. And 19 is only 1 off from 20, so it should only be 19 times 5 should be 5 off from 20 times 5, which is exactly what we just confirmed here. So we have that x is equal to -5, and that is the first part of our coordinate here. But we're not quite done yet, because we then also need to find y. So I'm going to choose to go ahead and resubstitute them in to my original equation where I had found y. So y is equal to 7 times -5 plus 41. 7 times -5 gets us -35. -35 plus 41 is going to get us 6. So we get that the y coordinate is +6. Now it is worth checking by resubstituting into the first equation to make sure this still works. So if I do 5 times -5 plus 2 times 6, does that indeed get us -13? Well, 5 times -5 is -25, 2 times 6 is +12. -25 plus +12 is indeed equal to -13, and we know we did it right. Go ahead and pause your video and try to do this next one yourself as well. So in this next one, I'm thinking that this first equation looks a little bit nicer to solve for y in, because if I have -2x plus y is equal to 9, the only step I need to do to get y by itself is to add 2x to both sides, because -2 plus 2x makes 0. I'm left with y is equal to 2x plus 9, and that gives me the perfect candidate to substitute into the second equation. So in the second equation, we have -3 times whatever y is equal to -28 minus 6x, and I'm going to replace y with what he is equal to, which is 2x plus 9. Now I'm ready to rock and roll solving for x. So to solve for x, I would first distribute that -3. That -3 times 2x gets us -6x. -3 times 9 gets us -27. And then drop down the rest, -28 minus 6x. Now I want to move all variables to one side, so I'm going to add 6x to both sides. -6 plus 6 makes 0 in both cases, and then I'm left with -27 is equal to -28, which is not true. So in this case, this would be no solution, or aka these equations would be inconsistent. I should find in these equations that if I were to solve for y on both, they should have the exact same slope with different intercepts, so that would be a way to check yourself. So in particular, I already solved for y in the first equation. If I were to solve the second equation, there's actually only one step, although for this first step, I'm first going to just rearrange that -28 minus 6x is the same thing as -6x minus 28. Then I would divide all three terms by -3. So that'd be y is equal to -6 divided by -3 is positive 2x. -28 divided by -3 is going to get us positive 28 thirds, which doesn't simplify nicely, but I know is not actually equal to 9. Therefore, I can confirm that both of these actually do indeed have the same slope, but different intercepts, so they should indeed be parallel lines who never touch, just like I got algebraically. Last but not least, go ahead and see if you can solve this equation yourself as well. So if I was looking for a good candidate to get a variable by itself in, I would say the second one is an excellent candidate, because if I have -7x plus y is equal to -34, how would I get y by itself? Well, I would undo adding -7x by adding positive 7x, since -7x plus positive 7x makes 0. And then I'm left with y is 7x minus 34. Then I would take a look at that first equation, -5x minus 2y is equal to -27, and I would rewrite it, but note that I'm going to replace y with what he is equal to, which in this case was found out to be 7x minus 34. Now I'm ready to rock and roll solving for x. -2 times positive 7 will give me -14x. Negative 2 times negative 34 will get me positive 68. Drop down the minus 5x, drop down the negative 27. Now I want to continue to combine like terms, so in particular, negative 5 minus 14 is going to get me negative 19x. Drop down the 68. And now that all like terms are combined within each side of the equal sign, I'm ready to move all constants to one side, all variables to the other. I'm going to go ahead and subtract 68 from both sides. I'm left with negative 19 is equal to, in this case, negative 19x, sorry. The x is still attached to negative 19 is equal to negative 95. And then just like before, that actually does go nicely into 19. So then I'm left with x is equal to positive 5, since a negative divided by a negative is a positive. That is the first part of my coordinate. I need to find the second part of my coordinate by resubstituting into what to find y. So I have y is equal to 7 times 5 minus 34. 7 times 5 is 35, minus 34 will leave me with 1. So I just confirm my solution is the 0.51. It might be worth double checking that solution by plugging both coordinates back into my other equation. So that'd be negative 5 times positive 5 minus 2 times 1 equals negative 27. Negative 5 times positive 5 is negative 25. Negative 2 times 1 is negative 2. And negative 25 minus 2 does indeed get me negative 27. So I know I just did it right because when I checked my work, it came out nicely. So to recap, in order to solve by substitution, you always need to solve one equation for one variable in terms of the other. For most of these examples, we ended up solving for y just because that's how the equation was set up. But keep in mind, you always could solve for x instead and then plug that into the other one too. That's totally fine. And then you want to solve the resulting single variable equation that you get. Then you want to plug that solution back into one of the original equations to find the second variable. Write your solution, and then you want to check your work by plugging back into the equation you haven't used yet in order to find that second variable, just to make sure it still works in that equation as well.